So in this video, I'm going to discuss chapter 22, electrostatic, and here we're going to discuss about concept of electric polarization. So electric polarization. Remember in the first video, I showed you a demo of I wrapped the balloon with my hair, right? And then balloon attracted pieces of tissue paper. What kind of a material is tissue papers? Tissue paper is made of paper. Is a paper electric conductor or insulator? Right, it's an insulator, right? Tissue paper is an insulator. In a previous video, we discussed about electric induction, and that's why you see you can induce the electric charge in a conductive material. But paper is insulator. How can a charged balloon attract a piece of insulated material? How does the electric force work? To understand that, then you need to understand the electrical polarization mechanism of a polarization. So let me share the video again that I did with attracting pieces of paper. Let me see. I have that here. Let me see again. Sorry. Share. Here. Oh, wait. Sorry. I gotta do that. Share the computer sound here. There you go. All right. You already saw this, but
action.
This is what I'm talking about right now.
Rubbing. Do it? Do you see my hair being stuck?
Yeah, it's starting to stick up.
Okay. All right, go closer.
Well, it's doing it a little bit.
All right.
Okay, so you saw that there was a piece of paper was attracted by the charged balloon. The balloon was charged by the friction with my hair, and then it can attract the electrical neutral insulated material. I can also show you this video. The sound is a little annoying, so I'm going to turn off the sound. Let's see. A similar idea. He just does more. So you can attract the pieces of paper. And now you wrap the balloon with iron, right? To charge the balloon. So now the balloon is charged. And when you put it on the wall, balloon is attracted to the wall. Is wall conductor or insulator? Yeah, so wall may have a metal inside, but surface of the wall is insulator, right? And charged balloon is somehow some kind of, there's an attractive electric force that attracts the balloon to the wall. And the wall is electrically neutral. And this is the hair comb and a piece of paper. And again, if you use the rub the hair comb, you can charge the hair comb, right? And charge the papers. So all these cases, the paper, wall, all these cases, they're all electrically neutral, and they're insulators, so they don't, you can't induce the charge. Then how can they be attracted? Sure, thank you for videoing. So how can they be attracted? We use that, so let's understand the charge polarization. Let me go into the slide directly. So let's see, I'm going to go into the slide here. I believe it's this one. Sure. So this is it. So why does the balloon stick to the wall? By rubbing the balloon, you charge the balloon. So balloon is now, by rubbing it, it's negatively charged. This way is better. Negatively charged. And then this negatively charged balloon sticks to the wall, right? Charge polarization. So insulated material do not have any free electrons. Conductors have a free electrons, which means the electron can move from one molecule to another molecule freely. Depends on the resistivity, but they can move. They can hop from one molecule to another molecule. So inside it, they can move around in the material. However, insulated material like a paper, wall, wood, cork, all these materials, they do have electrons in it, but these electrons are bounded around the atom or molecules. They cannot move, they cannot get out the molecules or atom. So what happens if I bring the charged object nearby, right? If I bring the charged object nearby. So let's say this atom before the charged object, it has a perfectly spherical shape. You have a nucleus in the center that has the positive protons in it, and then the electron clouds are perfectly making a nice spherical shape. But when you have a charged object, like let's say the negatively charged balloon comes nearby, then these electrons that are making a perfect circular pattern, circular shape of an atom or molecules, they feel the negative force coming externally. And the negatively charged electrons, feel the negative charged object that came nearby. So although they cannot move out from the atom or molecule, but they can shift it to the other side or inside the atom and molecule. Same thing, the nucleus inside, maybe that positive will be a little bit attracted towards it. So the shape of the molecule initially was like circular, but maybe it changes the shape that one side becomes more negative, the other side becomes positive. So overall of the molecule or atoms is still electrically neutral, same number of protons, same number of electrons in the atom or molecules, but they change the shape to have one side is more negative, the other side is more positive. And this is called electric polarization. All right. So here is the diagram. In A, the picture A, you have a perfectly spherical atom, the positive in the nucleus, positive charge in the nucleus, and then the negatively charged electron clouds surrounding it. But when you bring the positive object on, let's say, the left side of the atom, then the negatively charged electrons will be attracted. And although they're not moved out from the molecules, or atom, they're a little bit changing the shape of the cloud to make one side is more negative than the other side is positive. Okay. So you have an insight that overall, again, is a positive and negative is electrically neutral, but you have changed the shape to have a minus on one side and a positive on one side. Then you see the entire object. Could be a piece of paper here on the blue molecules, right? Then you add up overall all the molecules. Then you're going to see a little bit positive on one side, one surface of the object, and then a negative on the other side of the surface by adding up all the molecules. So again, the entire the object is still neutral, electrically neutral, but you can separate the charges that says one side is positive and negative. So when you bring the charged object nearby, like a balloon, right, negatively charged balloon, it sticks to the wall because the surface of the wall is slightly positive. And then the other side of the wall is slightly negative. It's not because the electrons actually moved out, but they change the shape. So it becomes rather like an elong shape, like something like this, right? Minus on one side and a positive on one side. By the way, the shape like this, you have a positive and negative that has some spacing in between, plus and minus like this, plus on one side and minus on one side. This is called electric dipole. So if you just have a one positive or one negative, whatever the charge, it could be 6 coulomb or 0.1 coulomb. If you have just a one charge, we call that's a monopole, just a regular charged object. But if you have a plus and minus, let's say 1 coulomb on one side, negative coulomb on the other side, that's separated with the space in between, we call that electrical dipole. Dipole. You have two polarities. Okay? But anyway, so you induce the dipole in the molecule. So the molecule becomes like each molecule becomes dipole, and you add up all of them, and one becomes positive and minus. So that's the charge polarization, and that is the reason why the balloon can stick to the wall. Let's see. So same thing happens with the comb, right? The hair comb, you wrap the hair comb, then becomes positively charged. And this is a piece of paper or tissue paper. Then one side of the tissue paper slightly but slightly becomes the negatively polarized, and then the other side becomes positively polarized. And then it gets attracted. Remember in a hydrogen model, the related calculation to compare the gravitational force and electric force. The electric force is so much stronger than a gravitational force. So you don't need to have much electrons to attract the paper. You know, you can like attract the paper there's a gravitational force that the paper has a weight that it wants to go down, but you can use the hair comb to bring up. And to do that, you don't need too much electrons. You don't need that much because the electrostatic force is so strong that you don't have to have that so many charge to bring up the paper. So I hope you see that the polarization is good enough to attract or even to stick the balloon onto the wall. And here's also another one that you see, the minus negatively charged one. And so this side becomes slightly more positive, stronger than the other one. And then it's not that electrons actually move out, but you polarize stronger here than the one here. Right? So it's like this. By the way, what happens? So the balloon is charged balloon. It sticks to the wall. But what if I put the charged balloon onto a doorknob that's made of metal? What happens to the balloon then? Do you see the same effect as the balloon stuck to the wall? Or you see something different motion when you stick the charged balloon onto a doorknob that's made of metal? You might want to think about that. All right. So that's the charge polarization, mechanism of charge polarization, and which means you polarize the molecules. I mentioned that let's say that here, the molecules are typically, let's imagine that molecules are spherical shape, like electrically symmetrical, geometrically symmetrical. But some molecules, by nature, naturally, they're a little polarized. Remember that water molecule is made of 2 hydrogen and 1 oxygen. And they share the electrons, right? Each hydrogen has 1 electrons, and then oxygen happens to have 2 open spots for the electrons. So each hydrogen sits onto the open spots of the oxygen. So that's how they share the electrons and forms the H2O a water molecule, right? But because of the those available, like electron clouds and stuff, hydrogen tends to sit on the oxygen like this, like a Mickey Mouse. So you have 2 hydrogens on the one side, and then oxygen on the other side, kind of. And I mentioned that hydrogen has the positive, and then oxygen is negative. So the over here is more negative. The side is going to be a little more positive. So water molecule by nature. So this is the water molecule. By nature, this is going to be positive and negative. So by nature, they act like polarized, naturally polarized. You don't need to have a charged object nearby. You just, because of the shape of the molecule, they act like an electric dipole itself. That's why the water or the fluid water, right? Not ice, where fluid water, there's a bunch of these charged, polarized water molecules. And you don't actually have a free electrons you don't have to have a free electrons in the water, because the water molecule itself is positive and negative. So when you bring some kind of a charged object in the water molecule, water fluid, then negative, let's say this is negative on my hand, then the positive side of the water molecule gets attracted. So you can move those water molecules because they're fluid, and then they can feel the electric force. So that's why they're conductors, if it's a fluid, right? Because there's kind of like one side is charged, a plus and minus by itself, naturally. And have you, let's see, microwave. So microwave, you put a food inside the microwave. You know the microwave is an electronic device. So some kind of electric thing is happening to heat up the food, right? But is the food charged? When we eat food, is it charged? No. Food is not charged, right? We just eat electrically, it should be electrically neutral. But how do we use that electronic device to heat up the electrically neutral food? Almost all the food contains water molecule, right? And then so inside the food, you have a water molecule. And then let's say this is the box of the microwave. So let's say the two sides. One side I make it positive, the other side I make it negative. So positive and negative. So the water molecule will be flipped, that negative on this side and positive on this side. And then what if I switch the positive and negative of the microwave? Then the water molecule inside the food flips. You switch again, flips. Flip, 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 flip. Water molecule. Each time you flip the external, the side of the microwave to be positive, minus, minus, positive, negative, negative, positive, positive, negative, negative, positive. You flip it, flip it, flip it, flip it. Fast frequency, right? Gigahertz or whatever the hertz you hear, right? You flip it fast. Then each time you flip it, water molecule flips, flip, flip, flip. That means you're increasing the kinetic energy of this water molecule. Increasing the kinetic energy, temperature increases, right? That's how you can heat up the food. You use the water molecules, the polarization of the water molecules, and then you raise the kinetic energy by changing the side of the external electric field that we're going to talk about in the next video. But you change the electric field, plus, minus, minus, plus, and then it flips. And then you raise the temperature of the food. That's how you warm up the food. Okay, so that's about it that I want to discuss for the charge polarization. You definitely want to think about what happens to the balloon, charged balloon, if you touch the doorknob instead of a wall. And what kind of a different mechanism or the same mechanism do you see? And explain with the physical law. Okay? Yeah, that's it. Okay, so I'll see you in the discussion.